Hey there, fellow deep diver. Ready to explore some chemistry?
I'm ready.
Today we're diving into the world of acids, bases, and salts.
They're everywhere. You encounter them every single day.
Okay, so we all know that lemon juice is sour, right?
Right.
But have you ever thought about why?
It's because of acids. Acids are generally sour.
Okay. What about things that are bitter, like coffee?
That bitter taste, that's often a sign of base.
So acids are sour and bases are bitter. Interesting. What about indigestion?
That burning feeling, that's usually caused by too much acid in your stomach.
Which is why antacids help. Right.
Yeah.
Because they're basic.
Exactly. Antacids neutralize the excess acid and relieve the discomfort.
So it's like a constant battle between acids and bases going on inside us.
You could say that. It's all about balance.
But how do we actually, study these acids and bases in a lab setting?
We use indicators.
Indicators.
Yeah, they're special substances that change color depending on whether they're in an acidic or basic environment.
Oh, so it's like they're telling us if something's an acid or a base just by changing color.
Exactly. Like litmus paper, for instance.
Litmus paper, right. It turns red in acids and blue in bases.
You got it. It's
Yeah.
a classic indicator. We also have synthetic indicators, though, like phenolphthalein.
Phenolphthalein, that's a mouthful. What does it do?
Phenolphthalein is colorless in acidic solutions, but turns pink in basic ones.
So it's like we're doing a science experiment and
Yeah.
we have all these mysterious liquids. We could use these indicators to quickly tell which ones are acids and which ones are bases just by looking at the color.
Precisely. It's a simple but powerful way to visualize what's happening chemically. And these reactions can get even more exciting.
Oh, like how?
Well, picture this. You drop an antacid tablet into a glass of water. What happens?
It fizzes, all those little bubbles.
Exactly. That fizzing is carbon dioxide gas being released. That's actually a key indicator of an acid-base reaction happening right before your eyes.
Wow. So that fizzing sensation, whether it's in an antacid or a science experiment, is a sign that an acid and a base are reacting with each other.
Absolutely. And that leads us to an important concept, neutralization.
Neutralization.
Yeah.
Does that mean one, destroys the other?
Not exactly. It's more like they cancel each other out.
Oh, okay.
When acids and bases react, they neutralize each other's effects. And as a result, they create salts and water.
So it's not a destruction, it's more like a transformation.
Yeah.
Come together to create something new.
Exactly. Neutralization is a fundamental chemical reaction, and it has so many implications, from something as simple as treating indigestion to balancing the pH of soil.
Speaking of pH, I know it's how we measure how acidic or basic something is, but can we go over how that works again?
Of course, the pH scale is basically a ruler for acidity and alkalinity.
Okay, and it goes from 0 to 14, right?
That's right. And 7 is neutral, like pure water.
Yeah.
Anything below 7 is acidic, and anything above 7 is basic.
So the further away you get from 7, the stronger the acid or base.
Exactly. Battery acid is super acidic, so it would be down near 0. And drain cleaner is very basic, so it would be up near 14.
Wow, so even small changes in pH can make a big difference.
They can. And pH is a really big deal. For example, our blood needs to stay within a very specific pH range to function. If it gets too acidic or too basic, it can be dangerous.
And acid rain, right? That has a low pH, and it can harm forests and lakes.
You got it. pH affects so many things around us.
So we've talked about acids, bases, and pH, but what about those mysterious salts? How do they fit in all of this?
Well, salts are basically the leftovers from that epic acid-base battle we were talking about.
Okay, so they're like the products of the reaction between acids and bases.
Exactly. Acids and bases react, they neutralize each other, and what's left behind? Salts, along with some water.
Gotcha. So are all salts the same, or are there different kinds?
There are all kinds of salts out there, each with their own unique properties and uses.
Like table salt.
Exactly. Table salt, or sodium chloride, is essential for flavoring our food, but it also plays a key role in various industrial processes.
Wow, salt. Not just for dinner anymore. What other kinds of salts are out there?
Well, there's baking soda.
Baking soda. That's a salt.
It is. It's sodium bicarbonate, and it's actually a mild base.
Huh. I never knew that. What else?
Then there's washing soda, or sodium carbonate. It's a stronger base, and it's often used in cleaning products.
So from baking to cleaning, salts are everywhere.
They really are, and we'll talk more about the fascinating world of salts and their many uses after a quick break. So we were talking about the many uses of salts.
Right. It's amazing how versatile they are.
And there's this really cool phenomenon associated with some salts. It's called water of crystallization.
Water of crystallization. Never heard of that.
Basically, some salts have water molecules trapped inside their crystal structure.
Wait, so even though they look dry, they actually have water hidden inside?
Yeah, exactly. And this trapped water, it can really change how the salt behaves. Well, take copper sulfate, for example. Hydrated copper sulfate crystals, the ones with water in them, are this beautiful blue color.
Okay.
But if you heat them up and drive off that water of crystallization, they turn white.
Whoa, really? Just from losing water?
Yep. It's like a chemistry magic trick.
That's wild. What happens if you add water back to the white crystals?
They turn blue again. The water molecules go right back into the crystal structure and the color returns.
So the water's like a little chameleon, changing the salt's appearance as it comes and goes.
That's a great way to put it. But water of crystallization isn't just about looks. It can also affect how well a salt dissolves in water.
So those hidden water molecules are pretty important then.
They are. They can really influence a salt's properties.
Hmm.
Now, this brings us to another interesting concept. Efflorescence.
Efflorescence.
Yeah, it's when a hydrated salt loses its water of crystallization when it's exposed to air. It basically dries out and leaves a powdery residue behind.
Oh, okay. Like when you see those white deposits on washing soda crystals?
That's exactly it. That's efflorescence in action.
Fascinating. So is there a term for the opposite? Like when a salt absorbs moisture from the air?
There is. It's called deliquescence.
Deliquescence. Okay, I think I'm getting it. So efflorescence is like the salt drying out, and deliquescence is like the salt absorbing moisture.
You got it. Some salts are so good at absorbing moisture that they'll actually dissolve in the water they pull from the air.
Wow. That's incredible.
Yeah, calcium chloride is a good example of that. It's super hygroscopic, meaning it loves water.
So it's important to know about these processes when you're storing different kinds of salts.
Definitely. It can really affect their quality and how long they last. Now, speaking of salts that interact with water in interesting ways, have you ever heard of plaster of Paris?
Plaster of Paris, isn't that what they use to make casts for broken bones?
That's the one. It's actually a type of salt called calcium sulfate hemihydrate.
Hemihydrate.
It means it has half a water molecule per formula unit. But when you add water to plaster of Paris, something really cool happens.
Oh, yeah.
It sets into a hard, solid mass. Basically, the water molecules go back into the crystal structure, and it forms gypsum, which is calcium sulfate dihydrate.
So it basically hardens because of a chemical reaction with water.
Precisely. That's why plaster of Paris is so useful. It's used in construction, art, and, of course, for those bone-setting casts you mentioned.
Wow, so salts really are more complex than I ever imagined.
They are, and we've only just begun to explore your fascinating world, but we'll have to save that for another deep dive.
So we've covered a lot of ground in this deep dive.
We have acids, bases, salts. It's amazing how much there is to learn about these compounds.
I know, right? And it's all connected.
It really is. Everything from that sour taste of a lemon to the way a plaster cast hardens, it all comes back to these fundamental chemical principles.
Let's do a quick recap just to make sure we're all on the same page.
Sounds good. So first, we talked about the difference between acids and bases. Acids are typically sour, bases are bitter, and they can react with each other in a process called neutralization.
Right. And neutralization produces salts and water.
Exactly. We also talked about indicators, those substances that change color depending on whether they're in an acidic or basic solution.
Like litmus paper turning red in acid. I always loved that in science class.
That's a classic. And then there's pH, which measures how acidic or basic something is.
The pH scale. It's amazing how important pH is for so many things, like our health and the environment.
It really is. And then we moved on to salts, which are so much more than just something you sprinkle on your food.
I know. They're used in baking, cleaning, and even medicine. Who knew salts could be so versatile?
And some salts even have water molecules trapped inside their crystal structure, which can affect their properties.
Water of crystallization, right? We talked about how that can change the color of a salt, like with copper sulfate.
Exactly. And we can't forget about efflorescence and deliquescence.
Right. Some salts lose water to the air while others absorb it. It's incredible how they interact with their surroundings.
It is. And then, to top it all off, we discussed plaster of Paris, a salt that hardens when you add water.
It's like magic, but it's all chemistry.
It all comes down to the interactions between atoms and molecules. It's fascinating, isn't it?
It really is. But you know, thinking about all this, something just occurred to me.
Oh, what's that?
We've talked about how dangerous it can be to mix water with concentrated acid. You know, how it can generate a lot of heat and even splatter.
Right, that's why it's so important to handle acids carefully.
But then I think about how essential water is to life, and how so many biological processes involve water interacting with acids and bases.
That's a great point. So how does nature manage that? How does it harness the power of these chemical reactions without things getting out of control?
It's like a delicate balancing act, a reminder that even in the seemingly simple world of chemistry, there is still so many mysteries to uncover.
Absolutely. So much to explore and so much to learn.
Well, on that note, I think we'll wrap up this deep dive. Thanks for joining us, everyone, and remember, keep those curious minds working.
Stay curious.